Recall the definition of derivative from one variable calculus. And this was that the derivative of a function of x is the limit as delta x goes to 0, f of x plus delta x minus f of x over delta x. And in Calc 1, you'd gone through, presumably, you've gone through a bunch of derivations on various derivative formulas based on this. If we look at this generalized to functions of more than one variable, we get the notion of partial derivative. A partial derivative, what we do is we choose one of the variables. So this ordinary derivative was denoted as df over dx. A partial derivative is denoted by this sort of curly d, partial derivative of f with respect to x. And this is defined to be the limit as delta x goes to 0 of f of x plus delta x y minus f of xy over delta x. So it sort of treats the y in this case as a constant. It doesn't change the y at all. It just does the derivative with respect to x. And the partial derivative with respect to y is defined the same way. This is the limit as delta y goes to 0 of f of x and then y plus delta y minus f of xy divided by delta y. So let's look at a couple examples of this. Let's say we've got the function f of xy equals xy plus x squared plus y squared, and let's take the partial derivative of f with respect to x. So this is the limit as delta x goes to 0 of, now the function, we're going to replace all the x's with x plus delta x. So we've got x plus delta x y plus x plus delta x squared plus y squared minus the original function, so xy plus x squared plus y squared, all divided by delta x. So now we're going to go and combine like terms. Let's distribute this stuff out first. So I see we've got limit as delta x goes to 0. And on this first part we've got xy plus delta xy. For the next term we FOIL that out. We've got x squared plus 2x delta x plus delta x squared plus y squared. And then distribute that minus sign through, minus xy minus x squared minus y squared. And this is all being divided by delta x. So now in the numerator, everything without a delta x should somehow cancel with something else. So I see if we look at the first term, we've got an xy and a negative xy. This delta xy will stay. We've got a positive x squared and a negative x squared, so those cancel. We've got a positive y squared and a negative y squared. Those cancel. So the only stuff left over here are things with delta x in them. So this is now limit as delta x goes to 0. And also now everything has a delta x in common, we can factor it out. And then what's left over is y plus 2x plus delta x. And this is all divided by delta x. And now the delta x's cancel. And we've got the limit delta x goes to 0 of y plus 2x plus delta x. And in the limit, this zeroes out, so we've got y plus 2x. So if you look back at the original function, and we think about how to do the partial derivative without going through this limit process here, if we're taking the partial derivative with respect to x, that means we're treating y as a constant. So if we take the derivative term by term on this, the derivative of the first term with respect to x, think of y as constant. Think of this as, instead of y times x, think of that as 7x. So its derivative with respect to x would just be 7, would be the coefficient. So the derivative of xy, well, y is constant, so the derivative of x is 1. We get just y for the first term. Next up, take the derivative of this with respect to x, and we get 2x. And again, y squared, well, y is constant, so if you take its derivative with respect to x, its derivative of a constant is 0. So we just get y plus 2x, which is the same thing as we got shorthand. So let's maybe look at a more involved example of a partial derivative. Let's say we've got f of x, y, is e to the x minus y squared. And we want to know the partial derivative of f with respect to y. Well, first off, this looks like an e to the u. So the derivative will be e to the u times, so we got e to the u times the derivative of the exponent. So the exponent is x minus y squared. Let's take the derivative of this with respect to y. So think of this like 3 minus y squared. Think of the x like some constant. So if we go to take the derivative of this, this will be 2 times 3 minus y to the first times negative 1 by the chain rule. So that's just when we take our derivative here, this is going to give us 2 times x minus y to the first times, by the chain rule, the derivative of the inside. And then we can rewrite this. We can simplify it to negative 2 x minus y e to the x minus y squared. That's the idea of partial derivative. And this works completely analogously in functions of 3 variables. Let's say we have f of x, y, z equals x, y squared, z cubed. And we want to know the partial of f with respect to z. Well, think of x and y as constants. So we're just going to do the derivative of the z part and let everything else sit. So this gives us 3x squared z squared. That's our partial with respect to z. Okay, now that we've got the idea of partial derivatives down, we can look at higher order derivatives. So we can look at, say, the second partial derivative of f with respect to x. And this just means, if we break this thing apart, this means the derivative with respect to x of the derivative with respect to x of the function f. So this means take the partial with respect to x, and then take the partial with respect to x again. And this is sometimes noted because these superscripts and subscripts can get kind of tedious to write out. This is also sometimes noted as f sub x x, indicating we took the partial with respect to x first and then with respect to x. We also have the second order mixed partials. So the second partial of f with respect to y and x. Well, if we break this apart the same way, the y is on the outside. So this is the partial with respect to y of the partial with respect to x of f. So we do the partial with respect to x first, then the partial with respect to y. And this is denoted with subscripts the same way. The one that's closer is the one that's done first. So first we take the partial with respect to x, and then we take its partial with respect to y. Let's look at a couple examples of this done. Let's say we have our function of x and y. Let's say this is x squared plus xy cubed. And let's say we want to find all 4 second order partial derivatives. So first up, let's find fx and fy. So this is the partial derivative with respect to x. So the first term is going to give us a 2x. The second one, we take the derivative with respect to x, and we get y cubed. Okay, now let's look at the partial with respect to y. Now this is just fy. This is the partial of the original function with respect to y. So the first term has no y's in it at all. Think of that like a constant. So its partial is 0. The second one, we do the power rule. We get 3xy squared. So that's our partial with respect to y. So let's look at fxx. This is the partial of f with respect to x, then with respect to x again. So this is just the first partial with respect to x, then with respect to x. And this one right here we actually just did. So this is 2x plus y cubed, and it's the partial derivative of this thing with respect to x. So we go through, we take the derivative of 2x, so we get 2, and then the second term is constant, so its derivative is 0. Let's look at fxy. So this is the partial of f with respect to x with respect to y. And what this is, so the fx we did previously is 2x plus y cubed. And we're going to take its partial now with respect to y. So the 2x is constant, so its derivative is 0. And this y cubed, we take its derivative with respect to y, and we get 3y squared. Let's do the other 2 mixed order partials. We also have fyy, and this is the partial of f with respect to y again. So the partial of f with respect to y we just did up here. So this is 3xy squared with respect to y. Now we take its partial, so we do the power rule, we get 6xy. And finally, the last mixed order partial, fyx. So this says do the partial of f with respect to y, then with respect to x. So fy, we just did a minute ago. This is 3xy squared. And we take its partial with respect to x. And we get 3y squared. And notice these two partial derivatives, despite the fact that the orders were reversed, came out to be the same answer. And for any reasonable function, for any function that we're going to be dealing with in this class, we have that if you switch the order of differentiation, these two are always the same as long as your function is reasonably nice. So if you get thrown off on the order, don't be too overly concerned about that. And we can do higher order derivatives than this. We can do third partial derivatives. So we've got, say, the third partial derivative of f with respect to x means we'll take the partial with respect to x, and then its partial with respect to x, and then its partial with respect to x. Or we can just shorthand that to fxxx. And the higher order mixed partial derivatives work the same way. Let's do one example of these and then we'll call it quits. Let's say we have f of xyz equals x y squared z cubed, and we want to know f y x z. So this says take the partial of f with respect to y, and then take its partial with respect to x and then z. That's a z. So the partial of f with respect to y is 2xy z cubed. Right? We treated x and z as constants and just did the y partial, which gave us 2y. And then we're going to take its partial with respect to x and then z. And so we take the partial of this thing with respect to x, that's just going to give us 2y z cubed. And then we haven't done the z partial yet. And then finally we take the partial with respect to z, and we get 6yz squared. So that's the idea of a partial derivative. We're going to generalize this in the coming sections, as we'll see later.